All right. So everyone, welcome to this week's monsoon seminar. And our speaker is Stefanie Kaboth-Bahr, and she is a new professor in paleoclimatology at the Freie Universität Berlin in Germany. She's a paleoclimatologist and a paleoceanographer with special interest in the interplay between low and high latitude climate processes, as well as marine and terrestrial teleconnections throughout the Cenozoic. She received her MSc in geoecology at the Technische University Berg Academy Freiburg in Germany in 2012, and her PhD in paleoclimatology in 2016 from Utrecht University in the Netherlands. Throughout her international PhD and postdoctoral research projects in Canada, Taiwan, and Germany, Stefanie gathered a strong and well-publicized background in paleoceanography and paleoclimate. Specifically, her research has focused on monsoonal variability, low to high latitude teleconnections, marine terrestrial interfaces, and the Plio-Pleistocene climate history on millennial to orbital timescales. For this, she combines methods from sedimentology, stratigraphy, micropaleontology, and geochemistry, and her most current research focuses on the interface between climate change and human evolution. And so I'm delighted today to have Stefanie here to talk about deciphering African monsoonal change during the past 500,000 years. All right, take over, Stefanie.
Thank you very much. Okay, good morning, everyone, or afternoon, or really late in the evening, wherever you are. Thank you very much for the opportunity to have the seminar talk today. Straight up, I like to acknowledge a whole range of people who have supported me through the years. So this work that I'm going to present is a synthesis of a lot of institutions I've worked at, with a lot of people I've worked with, and it wouldn't have been possible without them. So as for you, I hear some interferences. Is someone having the microphone on? All right. So what I like to talk about today is basically concentrating on African climate change throughout the last 500,000 years, give or take, because this has been a focus of my research since I started my PhD, and I have a tendency to always come back to this to some extent. So I like to give a little bit of an overview of what I've been doing, what I've been concentrating on, and as well as some of the limitations of the work I've done and the ways my collaborators and I have tried to kind of like attack these limitations in recent years. So first off, let's start with okay, I can't change. Can you see the switch of the slide?
Yes, it looks good now.
So the underlying issue that I've been working on for a couple of years now is how can we connect, or can we even connect, climatic change, particularly in Africa, to the human evolutionary record. The issues that come with that kind of topic is very beautifully outlined in this figure from Faced and published in 2021. On one hand, you have this very sparse fractionated record of the human evolutionary pathways that got us to the point where we are now, which is represented just by a handful of fossils, usually in certain regions, because they haven't looked in others or didn't find anything else. So there's a huge bias just to the archaeological record as is. And then there is a climatic part of this equation, which is just as complicated, because on one hand, which you can see here in the middle, you have the regional environmental records that usually are taken on land, that come with a whole set of issues, very often the age model issues, the sensitivity issues, and the proxy you use in trying to get out the climate sensitivity somehow. And last but not least, the issue of how you get from that regional scale somehow to the global scale that you in the end want to go to really make an assessment if on these long-term timescale that evolution takes, climatic variability existed that somehow matches up. And these issues have lasted for a very long time. There have been a multitude of processes being proposed to somehow link this up. The most common use is a simple fact of glacial interglacial change. It's set it in after the Pliocene extensively into the Pleistocene with these really strong glacial cycles that show up on a very regular basis. And it has simply turned out that that isn't really how it seems to match up for various of reasons. So it has been a lot of back and forth about how did ice volume increase during the Pleistocene and the climatic change associated with this have anything to do with the kind of evolutionary changes we see? Yes, no. And when I started my work in Potsdam some years back, I thought that the way it has been done previously might have been backwards. So instead of having a global idea that you're trying to somehow squeeze onto the African continent to get you a climatic framework, I kind of thought about maybe we should start from a different point of view. So this is basically the monsoonal change within Africa. It's the most common framework used to interpret climatic records, paleoclimatic records from the continent. So if you go into the literature just a couple of years back, it's usually, if you look on timescales of 100, 200, a million years, it's usually, oh yeah, the monsoonal belt basically moved up and down or contracted or increased, different variabilities of or variations of that argument. So when I started in Potsdam, I was like, how could we go about this a different way rather than go in with a basically pre-designed view on how this needs to work, since this is how it works today? Is there a different way to get an idea what the records actually show, how it might work? In order to do that, I pretty much went ahead and was like, okay, what am I going to need to do this? I need climate archives, a whole bunch of it, preferably. So, and they need to have basically two things. First, they need to be a proxy for wet-dry changes. No matter what the underlying method is, they need to have some kind of a recording of moist changes. And the other thing is they need to have an age model that is not just air. So it should be something that is half decently robust. So if you look to the continent of Africa itself, you're left with very few records that are long enough to make, let's say, the assessment of the last 500,000 years. So we recently, this is a study led by Verena Förster from Cologne, published a new record from Kaboth-Bahr, that is here in Ethiopia. And then there's a whole bunch of other records. One is from the Western Africa, which is Lake Bazumfi. Then you got Magadi and Malawi. And on the timescale of 500,000 years or more, that's it. That's pretty much what it boils down to in Africa, which is like 4 data points for an entire continent where evolution could have happened everywhere. So, and in order to kind of like fill all these gaps, we went about and had a look around Africa, because there's a whole lot of marine records that surround the continent that are argued to represent continental change. Foremost, one of these records are, for instance, these North Atlantic records, which are argued to represent dust changes. Dust changes is then linked back to the continent. Similar, the records from the Nile discharge, from the Nile Delta in the Levantine Basin, and that goes for a whole lot of other records that surround the continent and are argued to represent the moisture change in the hinterland. Rather, it is be through river runoff or dust or whatever the proxy might be. So what we basically went and did was like, okay, we accept that interpretation. We say, okay, this is exactly as they argue. The age models, we take them as is. We're not going to change anything. We assume whatever they did correctly, and we're using it that. And what we then basically did with all these records is make the assumption that the underlying most dominant mechanism is the same for all of them. So the sign which way these records change might change depending on where they are on the continent, but the mechanism that drives the change is the same for all of them. Just like in a way the monsoonal system as a conceptual idea. So then we chucked all these records into a principal component analysis. So if you have never heard of that or not entirely sure what it does, a principal component analysis, or a PCA, is pretty much a way to deconvolute a lot of data. So if you have like 11 data records and you make the assumption that there is something in there that is represented in all of them, you can run a PCA, and the first principal component, so the most dominant signal it kind of sorts out, is exactly that, a representation of the most dominant process that all the other records contribute to in a different variability. So the PCA was basically just a simplified statistical way trying to take all these records, marine terrestrial together, and then kind of like squeeze out one signal. that we can use and say, okay, this is the Pan-African climate signal that's the best representation over the last 500,000 years of what's going on in that continent, rather than relying on one record or two records, or select some of them and some not. So we just chuck them all together. What you get out if you do that is pretty much in this two part figure is the lower part. So that zigzag line going from 0 to 600, so left to right in age, is pretty much what you get out. So you have some zigzag going on, you have a very nice long-term swing that kind of goes with it, which if you compare it with orbital eccentricity, holds a lot of resemblance to this. So the first thing kind of gave us a good feeling, because we know that if you look at the monsoonal system, it is something that heavily on orbital timescale responds to insolation changes, so the orbital cycles. So any signal we should get out should preferably have something to do with insolation, otherwise it just didn't work. So the fact that it kind of has this 400 kiloyear swing, our first PCA, or the most dominant signal, is in a way was a good indication. So we looked at it, and then when you analyze each of the individual sites that went into the signal to see the sign of the change at the same point in time. So let's say at 200,000 years, if you go in there and check, you see that all the records I showed you before that are on the western part of the continent indicate at that point in time they're dry. I can't quantify how dry is at that point. I can only tell you they're indicating dry in terms of a change, a negative change from the median over the entire time frame. So they're signaling dry. At the same time, all of the other records on the other side, on the eastern side of Africa, signal wet. And that swing, this east-west swing, was persistent throughout the last 500,000 years, give or take. It's very, very much persistent. So we did some breakpoint analysis. You can see nicely where these phases basically cut off. We named them phase 1, 2, 4. And for the further explanation, I'm just going to concentrate on two phases just to highlight to you more visually what I mean when I say the continent kind of like switches east-west. So starting phase 2, this is the African continent with the sites I showed you before, just now colored. The red dots is dry, and the green, the blue dots is wet. So what you can see is that during phase 2, all the West Africans signaling wet conditions, and given their prospective proxy, whereas the eastern side predominantly signals broad. And when you then go switching from phase 2 in the eccentricity minima to the phase 3 in the eccentricity maxima, you get the exact opposite. It is really like 100% opposite of each other, how they react in the median change over this time in comparison to the median overall of the entire time frame. So it's a very clear east-west swap that happens. The thing is, this east-west swap is really hard to square with a simplified view on a monsoonal belt, either shifting or contracting, because this kind of position is always like it favors the hemispheres that warmest. So one way or the other, you have more of a north-south gradient to it rather than an east-west gradient. But the proxy data are clearly signaling otherwise. So with that kind of outcome, we went ahead and was like, okay, what else is there that can influence precipitation patterns in Africa, and to some extent override this annual change in the monsoonal belt that could give us the signal we are seeing based on the proxy record. So, and the example that we found that works would be actually the modern La Nina and El Nino variability that stems from basically SST variability or sea surface temperature variability in the Pacific realm. So now that gets us to the point of the Pacific is quite some distance from the African continent. How do you get from all the way Pacific and temperature changes at the surface to something changing in Africa in an east-west direction? So in order to square that, we looked at the different mechanisms that kind of like transcend change from ocean to ocean across the tropics, so basically ocean hopping if you want. And the thing that can do that is a water circulation, because the water circulation in its most simplified term is a belt of convection cells along the equator that covers not just the equator itself, but also the tropics and subtropics. And that belt moves east-west. It doesn't change north-south. It basically stays more or less within the tropical zone and just moves east-west, independent to the temperature changes of the oceans that are driving this. So depending on where you make the ocean warm, whether or not it's in the Indian Ocean or the Atlantic or the Pacific, that convection belt system moves. And the modern most dominant end member of changes within the water circulation are La Nina and El Nino, because this is one of the most profound changes that we can have temperature-wise in the oceans. This is a paper that got out just a couple of weeks ago, which I thought was fairly nicely summarizing this issue, particularly for East Africa, but be assured it also works for the other part of Africa. I just got to quickly go through the scheme so you can get somewhat of an overview about how this actually translates. So if you, in the case of an El Niño, you have a warming in that part of the Pacific. Interacted with that is the establishment of a so-called Indian Ocean positive dipole. So basically what it means is you're warming up that side of the Indian Ocean that's closest to East Africa. It's just these two things, the connection between the Indian Ocean and the Pacific Ocean is that way that El Niños usually go with a warming of the part of the Indian Ocean that will eventually cause convection in East Africa. So very strong convection events in East Africa are in most cases associated with a positive Indian Ocean dipole and pretty much sea surface warming just offshore. And the same goes the opposite way for the La Nina and negative Indian Ocean dipole. This is just an example, but this also translates into the Atlantic Ocean, as you can see here, because the sea surface temperatures in the Atlantic Ocean change with it as well. So this is interconnected. You change one, the rest will change eventually with it. And with it comes a very strong east-west pattern that transcends not just Africa, but transcends the entire tropical realm across the globe. And I'll get to that in a second. So the argument we made based on the record, the paleo record that we had, was this mechanism. Also, it is a modern concept and a process that theoretically exists only on decadal timeframe, that this is the best approximation of what we can find on long orbital timescales, looking at the data, because it explains the east-west shifting rather than simply associating change to a north-south stuff. If that is true, then you should also, from a paleoclimatic point of view, be able to actually align the signal, or align is maybe the wrong word, but find the signal reproduced in the, let's say, in the Pacific realm. So what we did is, this is the African signal I showed you before, so the Pan-African climate change signal. And we simply compared it to the temperature gradient across the Pacific, because this is what it defines water circulation changes in terms of El Nino and La Nina. So what we did is basically compare these two signals with, and H model issues aside, it becomes very clear that there's apparently a very good signal fit between these two things, despite the fact that they are very, very different things in the terms of how we got there. So one is a temperature record, which is a red line, and the other one is the Pan-African record we got out by chucking, I think, about 12 different records from the African continent and surrounds into a PCA. And there's a lot of climate variability in that are very close match. So that gave us somewhat of a feeling that water circulation changes as a carrier for insulation changes into the paleo-environment of Africa might be a much better framework to explain change there than a framework that relies either on CO2 changes or on ice volume changes, because they follow a very distinct 100 kiloyear pattern through this entire time frame with very much higher lows. But this long-term bow is something that neither the CO2 record nor the ice volume records hold. So this is something very specific that relates to a process that is directly linked to insolation rather than going away 6,000 kilometers away to find yourself an ice sheet that might have this impact. To us, it seemed when we looked at this data that it's easier to find a driver that relates specifically to the low latitudes than trying to explain this with a driver 6,000 miles away. However, why this is a good fit and why we thought that this is really a way that we could go back to the archaeological community and say, this is the best educated guess we can come up with that provides a Pan-African view and might be more helpful to you to compare or to assess the possibility of changes within the evolutionary pathways to this. It does come with a whole round of issues and limitations that need to be addressed. So one of the things we went about in order to kind of like check if this is remotely possible is by looking at the way on how to model this. So to get an objective kind of like reference to what we've been doing. And we talked to Phil Holden and Neil Edwards, and they run the Gini model for us for this time frame for the last 600,000 years. And we specifically asked them to run the model with basically the orbital configurations, and then look at the solar wind change, because that should be the representation of the Walker circulation for this time frame. So, and this is something, I'm a little bit confused where I am right now, but I get there in a second. Sorry. This is something that we then try to do. So hang on. So I'm going to jump forward to just finish that thought and then go back to this. Sorry. So this is basically the comparison we made, trying to kind of assess the reliability of what we have in terms of the proxy records and what the model gave out. So the model is basically the gray line, and overlying, I simply use the SST record from the Pacific, what I just showed you, that has a very close match to the African record, and it's a good representation of the Walker circulation from a proxy point of view. So, and what you can see is, again, H model issues aside, it's a very good fit, particularly towards the long-term bow that is in the model and that you get out of the proxy record. So while there is mismatches on, particularly on the precession timescale with the framework we're proposing, it does clearly highlight the fact that we can reproduce the signal even if you step away from the continent and go into the modeling. It is there, and it's fairly close to what we get from the continent, always keeping in mind that we're using unperfect records with an unperfect sensitivity to climate change, with unperfect H models. So just if you take on all the limitations that the individual records hold in comparison to this, it's still fairly good. With that in mind, since this is a global zonal wind PC1 that they used in order to represent the basically the wind component out of the model, we also looked across the globe then, because the context of, let's say, a global monsoonal system should be, if this is a global change that we can see in Africa following Walker circulation changes, it has to be everywhere else too. So using the same approach that I outlined for Africa, we went ahead and basically compared other low latitude records within roughly a 30 north to 30 south envelope, doing the exact same thing, which is what you can see here. So this is the equivalent of the first phase I showed you in Africa. So you can see West Africa wet, East Africa is mostly dry. And this is a representation of glacial interglacial change, of La Nina change within the modern precipitation change in relation to La Nina change. And on top, you see the proxy records for this time frame as outlined here. And it's the change it can signals using the same approach I outlined for Africa, just for a global scale. And what you can see is that if you just stick with the tropics and subtropics and go through the globe, you can see the records. The vast majority of them signal exactly what we would predict based on modern observational data. So, and that goes for the strong for the eccentricity minima, the La Nina position, and holds also true for the El Nino position. So you can see it in the model, you can see it everywhere else, at least for this time frame. So that gets us to the point of what else is out there when you want to kind of like bridge the gap from the climate stuff, assuming this holds for this time frame anyway. How can you bridge the gap then to, let's say, the archaeological record? So I'm going to quickly switch back to here. So what we did is, this is these three main phases of the eccentricity bow just outlined. So we go from a wet West Africa to a dry West Africa, and then to a wet West Africa again, going from old to young, from left to right in the figure. And we try to find other records that can kind of like signal this change. One thing we went about was pollen records. So these are the pie charts. The pollen are not represented just in Poaceae or something like that, but in terms of openness. So the more open it is, or the more closed it is. So the more open, it's more savanna-like in terms of more closed, more, let's say, a denser forest kind of conditions, these kind of swaps. And what you can see is that with the precipitation change we reconstructed also come as sparse as the data is, an indication that the vegetation change in accordance, going from more dense to more open, back to more dense. So it shifts the same way. So you can not just use the records that are supposed to represent wet dry, but you can also somewhat see it reflected in the pollen data. And then making that jump to getting us to the archaeological record, you can see these changes, these east-west changes also represented, let's say, in the fossil findings of mammals, because there's a lot more mammal findings than humans. So going, let's say, with hartebeest or African buffalo finding, they show the exact same thing. You get the same east-west kind of trending pattern again and again and again. And particularly, for instance, with the mammal findings, there have been a lot of the papers desperately trying to squeeze it into this north-south trending framework, and it just didn't work. And we really think that by proposing a framework that shifts more dominantly east-west, it might provide a better comparison on how to put this together. And since humans occupied similar ecosystems, or the same ecosystem and similar niches as some of these mammals, tracing their change might get us closer to what our ancestors might have experienced and then had to adapt to it in accordance. So long-term short is, we had a look at Africa as a whole, trying to see, going away from the simplified view of how the African climate changes, going to a way to assess by looking just at the pure data, and then going what modern kind of climatic framework works with this, trying that way to find an answer on how to best describe paleoclimatic change in Africa and on an entire continental scale for this time frame. However, as I said before, it comes to limitations. Also, we can find it in different records, in the archaeological records, in the pollen records, in the normal like wet dry proxy record. We can find in the model there is some of major cavities to this. And I like to kind of like use this seminar or this talk as a possibility to make a shout out to the community to start maybe looking at some of these issues in a way of trying to fix them somehow. So one of the things that we really experience is this only works if the walker circulation works the way it is modernly described. The moment you're changing that, so the moment, let's say, the Indian Ocean Pacific no longer have the same way of communicating with each other, let's say by changing the gateways that connect them. I'm not sure if everything I just said actually is going to hold. For the sake of it, we made a study last year trying to look at exactly that issue. So what we did is we looked at the Pleistocene. So I'm jumping a little bit time frames now, but it's just to make the argument. So I'm jumping to the time frame from 3.5 million years to 1.5 million years. Because there's been a lot of publications out there arguing that the onset of the modern water circulation was, and then fill in a number. And what we basically did is we looked at all the temperature records that are available. So this contains alkaline records, text 86 records, magnesium calcium records. This pertains to records based on planktic delta 18O, which also carries a strong temperature component. So we looked at these long-term records with a decent enough resolution and checked for their breaking point. And depending on, you can see just by the potpourri of really nice numbers here, depending on what you use and where you're looking, your definition of the onset of modern water circulation can vary drastically by nearly 1 million years, depending on where you are. So what this means, if nothing else, is that the changes within the water circulation, the further back in time you go, are not necessarily synchronous. I'm assuming synchronous change for the last 500,000 years, otherwise the concept wouldn't work. And since I can find it everywhere, it seems to kind of like boost us this argument. But the further back in time you go, the more tailing off this will be. If you just look at this for this about 2 million year frame that we used across the Pleistocene, your water circulation can change anywhere between around 3 million years, if you look around Indonesia, to about 1.5 million, depending on the other side of the Pacific. We think a lot of this is a representation of gateway changes. For instance, in this particular case, the Indonesian through flow changes. And that changes the way the oceans connect with each other. It also changes the way that change through the water circulation is then translated to one another. So the bottom line is, I don't think the concept I just showed you is transferable into time for a very long time, actually. Based on the paper, we made a guesstimate, if you want, that you may be able to translate this, let's say, up to the MPT, the mid-Pliocene transition, so 1 million years, give or take, and that's about it. And when you step before that, in all likelihood, the water circulation, the way we define it in the modern way, probably didn't exist. There was still a water circulation. There's no argument there. It's just, it might not have worked the same way it does today. So, and if you're changing that, then everything I just showed you goes out of the window really fast. So the first limitation for this concept is translation back in time. So if you're looking at evolutionary timescale, this becomes an issue because you cannot just take this as a blueprint and then go for the next 3.5 million years. This is not how this works, at least not in my view. So the one thing is we need a better understanding of when modern water circulation in that term was actually there to apply this framework. And depending on where you work, just by looking at these numbers, that can be a very different answer for very different people, depending on the methods you use. So this is one major issue in my mind on how we tackle water circulation changes if you want to go out of that 500,000 years, whether or not it's a assessment of African climate change or any other place within the tropics, since it appears to have a strong hold on all of them. So this is one issue. And then the other issue is the proxy records itself. So this going back to a slide I showed you beforehand. One of the issues are the age models. So the terrestrial records are usually inferior to the marine records because in the marine realm, we have delta 18O records, we can tune it. Damn, you're done, you have your age model. With the terrestrial records, that's very often not the case. A lot of these records, Malawi, for example, has a couple of age models. So you can pick and choose. Depending what timescale you're looking at, if you're staying with a long-term eccentricity boat, it doesn't really make much of a difference. We tried it out, we're using different age models for different sites, barely made a dent. But if you're looking on timescale, let's say on a precession timescale, it becomes a huge issue whether or not you take in that age model that is shifted 50,000 years relative to the other one. So there is very often non-consensus on the different sides which age model to use. Then comes the issue of the sensitivity of the proxies. So depending on what you use, that can be very different. One of the proxies that's very often used to assess African climate change is dust. However, dust is not just a function of hinterland moisture changes, it's also of wind gustiness. So depending on where you are, some of these processes are more dominant than in other places, but it plays a role. So taking any dust record from here and simply applying it as a one-on-one to the African hinterland might not be the way to go. Doesn't mean it's wrong. It's just, it comes with certain limitations to it. And since we just chucked all of these records in, assuming that they just represent purely moisture changes, this already carries a certain uncertainty that we cannot account for. So, and to kind of like as a last point of view, is really something I like to do, like as a shout out to the community, is really the records itself. Because depending on which records are used for this, the long-term pattern will hold, the short-term pattern might not. If you go on a precision scale and take half the records that are on this map, and the other half you don't, that pattern will look very differently on particularly these small time scales. So depending on the outcome you would like, in a way, you can do some modification simply by cherry picking one record over the other. So there is, by looking at all of this data, there is very often non-consensus over the robustness of one record over the other, even though they supposedly all show the same thing. And in that perspective, I like, basically as a last point, to put out a note for something I've been working on for many years, trying to get people to see these kind of records as a North African climate record, which most people do not, but I think it might be. And I like to just kind of like break lines for people to take a second look at it to see if we can maybe use these things in the future as well, or alongside the more established records, just to see if we can get a better understanding of the environmental change we can either through models or through other proxy records visualize. So, and this is basically represented in this figure. The black record is Kaboth-Bahr. This is a speedosine record that I'm pretty sure most of you are aware. The red thing underneath that looks just like it in a way is an XAF-based record from the Gulf of Cadiz. So the Gulf of Cadiz is basically the open sea area offshore of Portugal and South Spain. So after you exit Gibraltar, coming from the Mediterranean, that open ocean area is the Gulf of Cadiz. And when we looked at this record, we simply found that the signal that is represented in there that relates to the Mediterranean outflow is, HML issues aside, almost to a T, a representation of the monsoonal records we can find someplace else. These records, this close signal similarities, outbeat a lot of the records, traditional and more established records from the Levantine Basin, let's say the dust records that are there, or the titanium aluminum record that has been published from ODP site 967. These are records that are commonly used, yet the signal match we're getting out of the Gulf of Cadiz, even though it's really far away, is extremely close. And we consider this simply to be a representation of the fact that this outflow is an agent of monsoonal change, to particularly North African monsoonal change. Why would that be? I got to quickly explain this. If you look at basically the cross-section of the Mediterranean Sea as a whole, we have Gibraltar here on the left side, and the Levantine Basin on the right side, where the Nile directly goes in. So the Mediterranean is just like the open ocean. This is a thermaline circulation, so driven by density gradient changes. And it's extremely sensitive to fresh water, just like the Atlantic is whenever a Heinrich event hits. So it's simply like that. So if the Nile dumps a lot of fresh water in this thermohaline circulation, you're kind of like cutting it off. The outflow water is the water that at intermediate water that is fairly warm, fairly dense, exits the Mediterranean and goes into the Atlantic. It's basically, it is the countercurrent for the inflow that is required to stabilize the sea level in the Mediterranean, since the Mediterranean loses a lot of moisture due to evaporation and heating. So this outflow is a direct agent of whatever's going on in the Mediterranean, but not by sediment transport, simply by oceanographic changes, particularly density changes. So if you dump a lot of water, fresh water from the Nile into the Eastern Mediterranean, the outflow changes density. And with the density change comes a different way it interacts with the sediment outside in the Gulf of Cadiz that it sorts. Usually it blows over it because it's fairly dense, so it sets down on the sediment and it blows through it depending on how dense it is. So the less dense you make it, the less interaction we get, and vice versa. So this really nice XAF record I showed is pretty much a grain size reconstruction that shows the Mediterranean outflow water being on, off, depending on how much fresh water you're dumping into the Eastern Mediterranean, where it is sourced, depending of the Nile. So it's not depending on dust input or anything. It's just a matter of making it on, off, depending on how much fresh water you're dumping into the Eastern Mediterranean. So it's an extremely sensitive proxy record that signals monsoonal change as it has been captured in other records much closer than other traditional records. Yet this record is commonly not used, and even we did not use it for the simple reason that we're running into really very often issues with people not willing to accept that you can use something from the Atlantic that's very far away and has nothing to do with dust, still to trace back changes in Africa, particularly in the African monsoonal system. So to kind of like round up the talk, I hope I could give a bit of an overview about the way we try to assess African climate change over mostly the last 500,000 years. Rather than looking at one record or the other record, looking at everything that's there together, and then going from that perspective, trying to find a mechanism that could explain it, assuming that there is one. In the second part, I wanted to point out that while this is all nice and shiny and produces results that seem to be reproducible through a variety of archives and methods, it does come with a lot of hiccups. And these hiccups are long-term scales, they are on short-term scales, they are in the way you pick the records that you use. And in my mind, there's still a lot of things to do, and there needs to be more of a consensus within the community of what is robust enough to be used and what maybe is not robust enough to be used in this kind of study, because for now we just used everything. So at the end of the day, we would really like to establish or develop this idea into something to really give people a line that they can use to compare to, just like, let's say, a Delta 18O was kind of like given to the community and everybody has something to compare to in terms of glacial interglacial change. And we're trying, by looking at the water circulation as an answer to orbital changes in the monsoonal system, we're trying to kind of like develop piece by piece towards the aim of having that kind of line, but specifically for the low latitudes, not just for the high latitudes, because the interconnection that it seems is that a lot of the interference is about which way around these systems interact with each other boils down to the fact we don't have a good comparison line for the low latitudes. And I think long-term, that's something the community could work to in order to change. So, and this entire study that we propose is just as an idea giver of what might be possible if you look at it from a different way, more or less. So I hope I could like kind of give that overview to you and kind of like reach you with these issues. I'm happy to answer all these questions. Again, I'm very sorry I had to switch through the slides at some point. I got confused there. But thank you very much for your attention. If you have any questions, please let me know.
Great. Thank you very much, Stefanie. Does anyone have any questions? Yes, Jerome. Oh, sorry, you're just popping. You're welcome to switch on your videos if you like. While people are thinking about questions, I have a question. So on your maps that show on Africa that showed the proxy records and how there was the big switch between the East and the West, there was one site in the East that was always opposite. And I'm just wondering if there's anything peculiar or special about that site that might explain it. Or the other thing is the site just south of it that tracks with the East African, the other East African sites also seems to be in a slightly different environment that maybe that one's the one that's weird.
Yes. No, this is a perfect observation. So I'm going back to this slide to show it. These are the two modern precipitation outlines of what El Nino, La Nina do to Africa. So this is precipitation. And what you can see is these two sites here down are basically at the intersect of where these two system changes connect. So the record in particular, the one that always seems to be kind of like out of it is Malawi, to be specific. So it's a difficult record to begin with a certain age model issue after 250,000 years to begin with. So this is one issue, but it is at the intersect. And I think the more records you add, the more these regional issues come into play to a level where you see more likely privations of that are not a perfect match to that. Because it's just, this is a, I really need to be honest about, this is a extremely simplified version of something that is extremely complicated in reality. So, and that just with these couple of data points, you already see this regionality going through. So if you add another 10 data points to that, it's going to get even more complicated. However, I do not think the overall pattern of this east-west shift will change, because that is so systematic, not just in Africa, but also out of Africa, that I don't think that pattern is going to change so much. But the moment you add another data point in there, chances are it might be weird for whatever reason.
So if you were going to collect new records to add these new data points that might be weird, is there any particular place you might?
Yes.
So
there is this extremely huge area here, the heart of Africa, where there's nothing. So I some years back, there was this idea about the project in like Lake Chad, I think, the Paleo Lake there. So that would be an ideal position to get some information about these long-term changes. But it really very often fails to the point that we don't have the record, particularly on the continent, which is pretty much all of North Africa, more or less. The Western records, if you stick with the continental, boil down to Lake Bosumtwi for the long-term stuff, and that's pretty much it. So if I were have to like say, I would say a focus needs to be also put on the Western African, because Malawi, Magadi, and the entire DSP project with Lake Turkana, it's all East Africa, which is amazing work, but it's all in East Africa. And I know that it's because all the fossils are there and they're trying to make these connections, but at some point we're going to have to look at the other part of the continent, since evolution did not just happen in the African rift system. So if I would have to say, I would West Africa and North Africa need some data points. If not on the continent, then at least some records, marine records that tailor back more closely. So for instance, Cécile Planchet at the GFZ in Potsdam works on these paleo rivers in North Africa. And I think this is a beautiful approach that, if it can be translated to other areas, could give us ideas, let's say Western Mediterranean, and then trace back the paleo river from that side. It's a perfect way to do that, even if you can't drill on the continent or get records from there. Use that kind of approach to get the information regardless. So I think there are way around, but it's going to be a lot of work from the entire community to do this in a way.
Great, thank you. Does anyone else have any other questions? All right, well, I don't see any questions. And so,
I have a question.
oh, yes,
Yeah,
go right ahead.
sorry. Yes, I was wondering what the role of the Congo air boundary is in this whole story.
Yes. So we did everything I just showed. We also did in a more simple, in a more complex way for the last 20,000 years, 25,000 years, for that short time frame, because we have 14 sea dates on a lot of pollen records that are available. And what we found is that we can actually see the changes coming from the Congo air boundary, that you can trace that change as well. So it's in the data, and it's basically running with the eastern part. So you have the western part is doing thing, and the Congo east boundary actually goes with the other side of the continent. You can trace it and you can visualize it, but you have to scale down, and you need more records. So because the record density for that study is, I think, 2025 records, and that is about enough to kind of see it. So the approach we did for the big study is in nowhere, shape, or form able to visualize it, simply because of data lag. If you scale it down with a better chronology control, you can. It's there, but it still requires enough data sets, enough sensitivity to do it. But it seems to be there.
Okay, thank you.
You're most welcome.
All right, any other questions? If not, I want to thank you again, Stefanie, for this really interesting presentation. And with that, I'm going to stop the recording.